Wait. Rediscover. Alright.
Cool. Just put the slides up on your thing.
Yeah.
Alright.
Okay. Am I good to start? Cool. Welcome everyone for coming. We're just running through, currently this is the algebra half. Later on in the week on Friday, we'll be doing a calculus half. This entire thing is live streamed, it'll be recorded, it'll be on the MathSoc channel. You can find it all there, that's completely fine. There's also Supervision Day, 11th of August, 10 to 4, the location still to be confirmed. And there's a QR code as well if you want to scan that, just about confirming attendance and stuff.
That's Monday, week 11.
Yeah. And then as well, if I could get everyone to do the attendance form quickly for this session, that would be great. Cool. Thank you for doing that. So my name's Arun. I will be doing the vector spaces and the linear transformation, and then my friend Ewan will be covering eigenvalues, eigenvectors, probability, and stats. And that will be for the second half, the second hour. Other than that, I think we can just get started with vector spaces. So, firstly, the subspace theorem. If I have some S, let me switch my pen. If I have some S and is a subset of a vector space V, I will say it's a subspace if and only if these three conditions are true. So it contains a zero vector of V, it is closed under vector addition, and it's closed under scalar multiplication. So what do those things mean? Well, firstly, for closed under vector addition, it says that for any two vectors u and v that are from S, then the sum of them is also from S. And similarly, for closure under scalar multiplication, if I have any vector v that is S, then any lambda times v should also be from S. And let's just see an example of that. So suppose I have, okay. Yeah, I just touched that.
Just be careful of the plug.
Yeah. Okay. So suppose I have some set S, and it is vectors x1, x2, x3, and it is defined such that x1 plus 2x3 is greater than or equal to 0. So, how would I prove that S is a subspace of R3? Well, firstly, let's just go one by one. Firstly, it must contain the zero vector of V. So in this case, the zero vector here would be 0, 0, 0. And I want to verify that this is in fact a part of S. And so it must satisfy this condition here. So I know that 0 plus 2 times 0 equals 0, which is greater than or equal to 0, which satisfies this condition. So my zero vector of R3 is also part of S. So the zero vector condition, this first one here, check. Let's go to the next one. Is closed under vector addition. Well, how would I do that? So the easiest way is if I just define two vectors. So let's say I have a vector u, and I'm going to call my vector and I'm going to say it's ABC. And I'm going to have a vector v, and I'm going to have a vector v, and I'm going to call it PQR. So I know that because each of these individually are a part of S, I know that A plus 2C is greater than or equal to 0. And notice I'm just using this form again. Oops. And I also know that P plus 2R is greater than or equal to 0. And I'm going to use these two facts for my proof. So if I find, let's just go, let's add a new page. There you go. So again, I'll just rewrite that quickly. U is ABC, V is PQR. U plus V will be A plus P, B plus Q, C plus R. Hopefully there's no issues there. I've just added them together. And I want to show that this is a part of S. So my condition for S is that x1 plus 2x3 is greater than or equal to 0. So I will show A plus P. I'll have A plus P plus 2 C plus R. And that is just me using that same form earlier. I can... Okay. I can split this back into A plus 2C. So I've just taken this term and this term, plus P plus 2R. And notice, from what I said earlier, that each of these individually are greater than or equal to 0. If I know that this term is greater than or equal to 0, and I know that this term is greater than or equal to 0, then this entire set, or this entire expression, must be greater than or equal to 0. And as such, it satisfies this last condition here. Or it satisfies that x1 plus 2x3 is greater than or equal to 0 when I add them together. Finally, I will test that. I will test for scalar multiplication, so I'll quickly show you this. So this is just what I was showing earlier. It's testing the 0 vector, and it's testing this. Then, last thing I want to check, let's add another page. Let's bring back my vector u, and I'll call it ABC again, why not? And now I know that A plus 2C is greater than or equal to 0. And I want to show that, or I want to see, is lambda u, is this part of S? So I know that lambda u is lambda A, lambda B, lambda C. And then I'm trying to show that lambda A plus lambda, so let's say, plus 2 lambda C. And I want to see, is this greater than or equal to 0? Well, firstly, I notice that I can factor out lambda. So I get A plus 2, lambda times A plus 2C. Sorry. Is greater than or equal, or let's say, just that for now.
Just some issue with the streaming.
Yeah.
You Sorry about this, guys.
Restart the mirroring.
Yeah,
Just pop up.
give it another go. Yep. Go ahead.
Everything all good?
I think so.
Okay. Cool. Sorry about that. Let's continue. So I have lambda, and then I have A plus 2C. I already know, oops. I know that this bit here, I know this is greater than or equal to 0. But do I know this entire expression is? Well, I know that because I'm multiplying these, this will be greater than or equal to 0 only if my lambda is also greater than or equal to 0. Because if my lambda is negative, then of course I have a negative number times a positive number, which will be negative. And this will be less than 0 in this case. So we say that S is not closed under scalar multiplication, and thus it is not a subspace. And often you'll sometimes be asked to show a counterexample, and in this case they exactly show just a scalar of -1. So that was the case I was saying. What if my lambda is negative? So -1, you could do any negative number here, it should work the same. And from this, you can prove that it is not closed under scalar multiplication. Is there any questions with that? I feel it's pretty simple. Cool.
It's still working.
Yeah.
Restart the screen capture. Wait, so It's not off the screen mirroring. It's still streaming it. Why is it still showing up? Like, where is the screen mirroring? Is it now? Or okay.
So maybe like, yeah, just restart it. So frustrating.
Just a second, guys.
Okay,
It's
put that,
not
on, put that on the bottom.
working.
Yeah.
Yes, yeah. Then
Okay. Now let's give it a go. And then if we... Is there any way to flip back to OBS?
no, you can't.
Oh, okay.
Okay. Again, sorry about that. Hopefully we can continue. So I think that was this question. That was, yeah. So S is not a subspace, not closed under scalar multiplication. I believe that is all. Let's go to another example. Let's prove the other case that we haven't shown yet. What if we want to show that something is closed under scalar multiplication? Well, how do we go about that? Well, it was like I was saying. I can just show you this slide. Let's get this laser pointer. So I have any vector v and it's going to be x, y, z. It doesn't really matter what. And I have v and I have some scalar lambda. Then I'm going to consider lambda times v. So that is just as I said earlier. So it is lambda times each of those terms. We know that here is my expression here. So x1 squared minus x2 squared equals x3 squared. And so just because we call this x, y, z, x squared minus y squared equals z squared. Hopefully that's fine. And once I multiply lambda, I just swap all of these terms out with a lambda. So I have lambda x squared minus lambda y squared. Of course, from this, I can just factor out a lambda. And I know that x squared minus y squared equals z squared, which is this term here. And so I can just rewrite it like this. And thus, we're back to our first thing. This is our condition to show that it's closed under scalar multiplication, because this is just this term again. Hopefully that's simple as well. Any questions for that? Hopefully that's all okay. Cool. I think that's that for that. Okay, now we're into spans. So what is a span? Well, consider, let's say I have a subset S in a vector space. Anything that can be made of linear combinations of these vectors, and so linear combination is some constant lambda times each vector, so lambda 1 times v1, where this is my set S, so it's a bunch of vectors v. So lambda 1 times v1, lambda 2 times v2, plus all of these, lambda n times vn. Anything in that form is the span of some set S. So what can I do with that? Well, if I have this is just another way to notate it, same thing. And we say the span of S is V. S is called a spanning set. Don't think there's anything else I need to say there. I think I can just show the question. So consider the vectors in R3, and I have all these 4 vectors here. Prove that B is in the span of V1, V2, V3. Well, let's see exactly what that means. So I know that, and let's go back. So if B is in the span of these, then B must be, like I said, some linear combination of all these vectors here. So I know that B must be, let's say, let's call them different letters. So let's say alpha times the vector 1, negative 1, 2, plus beta of 1, 2, 5, plus gamma of 2, negative 3, 3, should equal my vector B. So it's negative 1, 6, 3. Now this expression might look somewhat familiar because this is exactly how we'd write a system of linear equations. And I have 3 equations here. So I'd have, well, my first equation would be alpha plus beta plus 2 gamma equals negative 1. And you can see I could formulate the rest of these very similarly. And so I have these 3 equations here. And we actually already have lots of tools to solve this. And the easiest way, or the first way that comes to my mind at least, is using row echelon form. So I can convert these vectors into, so you can see these vectors v1 like this. I can rewrite those same vectors into a augmented matrix. And this augmented matrix I can solve using Gaussian elimination and stuff, and I can get something like this. And so how do we interpret this result? Well, we have this bottom row of zeros. This does not have one unique solution, but there exists at least one solution. Oops. There is at least one solution, is what this is telling us, for this set, so lambda, or for this equation, sorry, and hence we say B is in the span of S. There is a solution for lambda 1, lambda 2, lambda 3, such that B is a solution of that. Does that make sense to everyone? Cool. And let's go, there's actually another part to this question. Is V1, V2, V3 a spanning set of R3? So what does that mean? Well, that would imply, if it's a spanning set of R3, that this combination of vectors can produce any vector in R3. And so instead of setting it to just equal to B, what if I set it equal to something like X, Y, Z, or just any three random, like, I don't know, symbols? Then I can apply the exact same thing. So here we have lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 equals just some vector x, y, z. This is the set of all possible numbers in R3, where again x, y, z are all real numbers. Well, again, they've kind of skipped a step, but it's just showing that I can apply Gaussian elimination, and I can just get this expression here. And then from this, I can figure out what is the solutions. And I know that this will only ever have solutions if this term here is 0. And why is that? Well, let's just think about that last line. That last line is essentially just saying, if I have these lambda 1, it's saying this is 0 lambda 1 plus 0 lambda 1 plus 0 lambda 2 plus 0 lambda 3 equals this stuff. In other words, 0 equals negative 3x minus y plus z. And of course, if these values here were equal to any other constant, then this equation just doesn't make sense. So I'm saying like 0 equals 2. That doesn't make sense. So a solution only exists if this condition is satisfied. And so we find that not all vectors in R3 satisfy this. Oops. This condition is not always true. It is not a spanning set. Does that make sense to everyone? Any questions? Cool. And then we're on to linear independence. So you can see a very similar equation, but we're using it in a different context this time. So again, considering a set S, which is vectors v1 to vn, vector space V over the field F. S, we say, is linearly independent, so the set of vectors is linearly independent if the equation lambda 1 v1 plus blah 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 lambda 2 v2 lambda 3 v3 all the way to lambda n vn equals the 0 vector has only one solution, and that only solution is when all of the constants, or the coefficients, sorry, they're all equal to 0. If this is the case, then we say this set S entirely is linearly independent. Another way to think about this is, because of course you can rearrange this equation, you could say something like v1 is equal to, and I could rearrange these all to the other side, and I could divide by lambda 1, and I just get some new set of constants. So I'm just going to call it alpha 1 v2 plus alpha, so alpha 2 plus alpha 3 v3 plus alpha 4 v4. And this is me rearranging my equation here. And essentially another way to think about it is no vector is a combination or a linear combination of any of the other vectors. They are all unique. And so they're saying here, if a solution exists where there is at least one lambda which is not equal to 0, then S is linearly dependent. And that's just the opposite. And they say something here, if one of the vectors is in S is a linear combination of the other vectors, which is what I was saying in my rearranging. And some other interesting properties. what if I had one of these vectors, let's say v1, let's say v1 was the 0 vector. What about that? Well, in that case, this would be 0, and all of these, I mean, it doesn't really matter what these are. I could set all of these coefficients, so I could set lambda 2 equals lambda 3. I'll do this on a new page, actually, just so it's a little clearer. So if I have lambda 1 v1 plus lambda 2 v2 plus all the way to lambda n vn equals 0. So if my v1 vector equaled the 0 vector, then I would get the case that I would have lambda 1 times my 0 vector plus, and I'm going to set lambda 2 equal lambda 3 equal all the way to lambda n, and they all are 0. What happens here? Well, this coefficient is 0, this coefficient is 0, all of these are 0, this one's 0. Everything here goes to 0. And I'm only left with this term here, so I would have this lambda 1 times the 0 vector equals 0 vector. Notice here, for my lambda 1, this lambda 1 could take any value it wants, and this expression would still be true, because any constant lambda times the 0 vector is the 0 vector again. So what does that mean? Well, that tells us that if the vector 0 is in any of the set of vectors, the set is immediately linearly dependent. We don't have to check anything else. If 0 is one of them, then the entire set is linearly dependent because of this one condition here. And I suppose another thing that they wrote here as well is that if two vectors are linearly independent, then they're not equal or parallel. Because remember, if something's equal or parallel, then I would say that it is a linear combination of the others. So if I have something, if v2 is parallel to v1, then v2 must be some scalar multiple of v1. Or similarly, if v2 is equal to v1, then v2, the scalar multiple is just 1 v1. So if they're linearly independent, then they can't be equal or parallel. And then we get some other interesting properties here. If the set is linearly independent, then when I write it in row echelon form, it is linearly independent if there are no non-leading columns. So what do I mean by that? Well, I think it's good if I consider another example here. So let's consider the vectors. Let's consider the vectors like 1, 2, and then maybe like 2, 4. Clearly, you can see that these two are scalar multiples of each other, because I can just multiply this by 2, and I get the other one. Well, what if I write this in a matrix like this? So I have this column is 1, 2, this column is 2, 4. Well, when I apply Gaussian elimination, I will get the result, and this is just doing row 2 is minus 2 row 1. So I get 1, 2, 0, 0. Notice that what I've done here, and this is interesting to see, I've taken these vectors and I've essentially rewritten them as scalar multiples of everything else. And because I've fully eliminated it, this row is going to 0. In other words, this is a non-leading column. What that means is I have rewritten, or I am capable of rewriting one of these vectors, or one or multiple, depending on how many, as a linear combination of the others, which means that because I have done that, the set if non-leading columns exist, so notice here, a non-leading column exists, then the set is linearly dependent. Does that make sense to everyone? Yeah? Cool. And the last bit is, we can also look at the determinant of the matrix, and if the determinant is 0, then the vectors are linearly dependent. A non-zero determinant means the set is linearly independent. Let's go back to this. So I will just, let's move this. Let's move that there. So let's take this. Maybe you remember that if I wanted to find the determinant of a matrix in row echelon form, so I can just take the product of the diagonal. In this case here, okay, I'll just leave that. If I take the product of the diagonal here, this, as long as I have 1, 0 here, then the product of this diagonal would be 0, which causes this case here. If the determinant is 0, and I can find that determinant from the product of the diagonal, then the vectors are linearly independent, or linearly dependent, which is what I saw here from this example. And the other case, oops, let's rub this out. What if the determinant was non-zero? Well, that would mean that all of these have terms here, and if all of these have terms, then the determinant, if the entire diagonal has terms, that means there is no non-leading column. So all the columns are leading columns here. There would be, let's rub this out. Not that it does form this, but if I had some other case, maybe it forms something like this, and I have leading columns, and the determinant is non-zero. And so I can say that this is linearly independent. Is that cool with everyone? That makes sense? Cool. Let's consider a case. Okay. Let's go back to this. So if I know that B here is vectors u, v, w, and I'm going to say this is linearly independent in R3. So I have these sets S, S1, S2, S3, and I want to determine with reasons, are these linearly independent or not? So let's just take this first one. I can go on. So this first one here, this is pretty simple. U1 minus V, lambda is real. And I would have lambda u minus V. So there's literally just one term here. So it's lambda of that equals 0. And I want to show that the only solution to this is if lambda equals 0. Well, I can rewrite this, and I know that this is the same as saying, actually I can, before that, let's establish that we know that this set, UVW, is linearly independent. And so U and V can't be equal. So U minus V is non-zero. The reason that's important is because for this equation to be true, either this could be 0, in which case it doesn't matter what lambda takes, or this is 0. But because we know that U minus V is non-zero, and we know that because they are not equal, because it is linearly independent, then S1 is linearly independent. The only way this works is if lambda equals 0, because this is a non-zero vector. Then S2 is U minus V, V minus W. So we have two constants, lambda 1, lambda 2. U minus V, V minus W equals 0 vector. I can just expand this and regroup it for U, V, and W. They regroup this for U, V, and W. And I want to see how would I get this solution to have a 0? Well, we already know that the set of U, V, and W is linearly independent. So we know the only solution where this is the case is if this term and this term and this term all equal 0. This middle term is a little problematic because I'm just saying, what, lambda 2 minus lambda 1 equals 0. Well, that is true for any case where I have lambda 2 equals lambda 1. So if I'm just looking at this does not necessarily have to be 0. But I can look at the others, and the others tell me a lot more. So I know this term is 0, and I know this term is 0. So I know lambda 1 is 0, and I know negative lambda 2 is 0, so lambda 2 is 0. And so again, S2 is linearly independent. Does that make sense? Cool. Then we're going to go to S3. So S3, I've got 3 vectors now, lambda 1, lambda 2, lambda 3, and then again, I can just sub those in. So lambda 1, lambda 2, lambda 3, multiplied by each of the vectors in my set, equals 0 vector. And once again, I'm trying to show that the only solution to this is if this and this and this equal 0. So, again, same trick. We're going to group it for u, v, and w. And now I know that this equals this equals this equals 0. Because, like I said earlier, the set of u, v, and w, of u, v, and w, these all have to be, this is linearly independent. So if I was to write this out with coefficients, so I'll be saying like alpha u plus, or alpha 1u plus alpha 2v plus alpha 3w equals 0. Only solution to this is when all of these equal 0. And so here, I will have this equals 0, this equals 0, this equals 0. And that's what they've written here. And by solving these equations, they're probably not too hard to solve, you can find that lambda 1 equals lambda 2 equals lambda 3. This is the only condition though. And this is a little tricky because, of course, if I set this all equal to 0, then everything's fine. But the condition for something to be linearly independent is that this equaling 0 is the only solution. And in fact, we find that, well, if all they have to do is be equal to each other, I can just set this equal to 1, and all of a sudden it's true again. They're equal to 0. And this is a problem, and so this is not the only solution. So we say it is linearly dependent. Does that make sense? There's this case for lambda 1, lambda 2, lambda 3 that are not all equal to 0, where it is still, the product of these is still equal to the 0 vector. Does that make sense? Cool. Okay, bases and dimensions. So I'm going to say let B be a set for a vector space V. If B is linearly independent and a spanning set for V, so both of these are true, so these are the two things we just covered, linearly independent and a spanning set. If both of these are true, then B is called a basis. And we say the dimensions is this dim V. Number of vectors in a basis gives us the dimension for V. So, here we have a neat little trick. The set cannot be linearly independent if there are more, oh, sorry, let's start with this first. Set cannot be linearly independent if there are more vectors than dimensions in a set. So the easiest way I could think about explaining this is, let's consider like R2, for example. Obviously, I'd have vectors 1, 0, and 0, 1. And those two are basis. But there's no other vector I could add that would still be linearly independent from the other two, because these two already make up everything in R2. So, here we have a neat little trick. If two of these conditions are true, then a set is a basis. So the number of vectors in the set is equal to the dimensions of V. The set is linearly independent, or the set is a spanning set for V. As long as we have two of these to be true, then the set is a basis. So how can we apply this? This is actually a really interesting question. I will show it. I will not go through it in detail because it does take a little bit of effort to try and calculate, but it's still a really interesting question. So we have this field, and it has these elements 0, 1, alpha, beta. And addition and multiplication are defined as following. And you can have a little table there. I'm not going to read all that out. And I've got three vectors here, b1, b2, b3. And you can see they are 1 alpha beta, beta 1, 1, and 1, 0 alpha. I want to show that this b1, b2, b3 is a basis for f3. So, I'm going to consider this matrix, b1, b2, b3, in row echelon form, and I convert it to this. And so this is just testing linear independence, because remember we talked about if there's leading or non-leading column, we can tell if they are independent or dependent. So this step, or getting from here to here, obviously requires Gaussian elimination. Obviously you have to be really careful when you do this, because addition and multiplication are defined in this table. And you have to keep that in mind when you're doing your Gaussian to try and get to row echelon form. And that's really important. But regardless, we can get to this, and I've kind of just skipped ahead a little bit. You can do this, and like your first step would be, for example, what's it? Like your first step would still be eliminating all these rows. Oops. You'd still be eliminating each of these rows one by one. And so I'll just skip to this. Here's my row echelon form. Since there are no non-leading columns, you can see this, no non-leading columns, set is linearly independent, which is good. And we have another thing. We know that this is F3, and we have 3 vectors here, and 3 vectors in the set. And so, the dimensions of F3 is 3, and we have 3 vectors. So, these two, we have this is true, and we have this is true. So we don't really need a proof for this bottom one. We have 2 of these 3 conditions are true. As a result, we know that B1, B2, B3 must be a basis. Does that make sense? Any questions? Cool. And so, part B. Explain why this is a spanning set such not a basis. So firstly, dimensions of F3 is 3. The set has 4 vectors. So the set is not linearly dependent, so it's not a basis. Hopefully that makes sense. Then let's consider the linear combination of this set. And so, because we're trying to prove that it's a spanning set. So not a basis, hopefully pretty trivial. 4 vectors, dimensions of F3 is 3. Let's consider the linear combination. Lambda 1 times the first term, lambda 2 times the next term, lambda 3 times the next term, lambda 4 times the next term. And again, we're doing the same thing as earlier. We're just going to group it for B1, B2, B3. So, we have considered some linear combination, and this is what we had earlier. So we know these 3 vectors are a basis. We had that initially in our first part, that these 2 conditions of 2 out of 3 conditions are fulfilled, and so this B1, B2, B3, they must be a basis. Oops, sorry. So I take this, and I want to get to this some linear combination. I know this must equal, if this equals 0, then the only solution is when mu1, mu2, mu3 are all equal to 0. And so I want to try and get this one into this form. And so the way I would do that is just by saying lambda 1 plus lambda 2 equals equals mu1. I know lambda 2 plus lambda 3 equals mu2. And I have lambda 3 plus lambda 4 equals mu3. So I ran a bit of space there. That's just me saying this term here is my mu1. This term here is my mu2. This term here is my mu3. I'm trying to get it into this form because I know this shows that it spans the whole set. And they show you, I mean, I didn't end up solving this. You can solve these equations here for all your lambdas. Since you do have 4 terms here, you have lambda 1, 2, 3, and 4, but you only have 3 equations. So we can just set lambda 2 here to be 0. It doesn't really matter what value you choose, it can be anything. You could also have set a different one to 0 as long as you end up solving the equations. That's completely fine too. There's also lots of different ways to solve it. You can Gaussian, you can just rearrange these, all of those are fine. So they just rewrite each lambda 1, lambda 2, lambda 3, lambda 4, and we can simplify into this. Hopefully, does everything up to here, does up to there make sense with everyone? Okay. So I've chosen my lambdas such that they will end up giving me this combination. And I know this, or I know that the set B1, B2, B3 spans my field. And so this original one, so my original set here would do the same thing, because I can just rewrite it as some linear combination of each of my three vectors. So it is a spanning set, as it is, or this set is a spanning set because it's a basis. So this one must also be a spanning set. Does that make sense? Okay. Are there any questions so far, or everything all good? Yeah?
Why do you set lambda 2 equals 0?
We have originally, so we know that we want to get it into this form of some constant time b1, some constant time b2, some constant time b3, because we know if I can express it like that, that is the span, right? It's some linear combination of each of those. Here, I had these three equations. I knew this bit, I wanted to get to mu1. This bit, I wanted to get to mu2. That was horrible there. And this bit, I want to get to mu3. Notice I have 4 variables here, lambda 1, 2, 3, and 4. But I have 3 equations. So maybe I should write this out a little neater. And I'm going to cheat by having this on the side so I can write this out properly. Lambda 1 plus lambda 2 equals mu1. Lambda 2 plus lambda 3 equals mu2. And lambda 3 plus lambda 4 equals mu3. Because I want to solve for each lambda, but I have 4 unknowns and 3 equations. And so I'm not going to be able to solve this for a value for each of them. I'm going to have to assign one of them a random value. I could have chosen any value. So here in this example, lambda 2 went to 0. I did not have to do that. I could have done lambda 2 to be some other constant. I could have made lambda 3 to be 0. I could have done anything, but I just need to fix one of them to some random value, and then I will solve for the rest of them in terms of that. Does that make sense?
Yeah, thank you.
Yeah. Okay. So coordinate vectors. I believe this is 1, 2, 4, 1 only. I mean, correct if I'm wrong, but I will still go through this anyway. So if we have a vector v, and we can say as a linear combination of a basis. Let me go back to my little thingo. Coefficient required to make v a coordinate vector. So I want to find the coordinate vector of v. So it is this with respect to this basis. Well, what does that mean? Well, essentially it is just saying that I have this basis. I know I want some amount of this vector, some amount of this vector, and some amount of this vector to get me this. And an easier example to think of if I had like 0, 0, 1, sorry, let me actually go in order. 1, 0, 0, 0, 1, 0, 0, 0, 1. If I had something like this, then the way I would do it is I'd make up some of this, some of this, some of this to get, so it would be 10 of the first one, and then I have 3 of the next one, etc. Hopefully you can see that is just forming this 10, 3, 21. I want to do the same thing here. And again, that is just me essentially just saying I'll have alpha of 1, 2, 5 plus beta of 1, 1, 0 plus some other, let's say gamma of 4, negative 1, 3 equals 10, 3, 21. And then you can probably already see where this is going. I'm going to do another Gaussian. Exact same thing. You can see I have my vectors like this. I just pop them into my columns, have this vector that I'm solving for be my 4th one, and then a row echelon form, and then really easily I can just find for each of my lambda 1, lambda 2, lambda 3. So our coordinate vector of this point here, in terms of this basis, or let's say with respect to this basis, is 3, negative 1, 2. Is there any question with that? Seems simple enough. Perfect. And I believe that takes us on to linear transformations. So linear transformations, you'll end up seeing that I should be able to breeze through this fairly quickly. It's a lot of the same stuff, just reused. So, linear transformation, so linear maps or linear whatever. So let's say I have some function and take me from v to w. Both of these are vector spaces. Earlier we said things had to, or subspaces had to be closed under addition and multiplication, or vector addition, scalar multiplication. Here we say they're preserved. So linear functions, linears are functions, we say they're preserved, they're not closed. But linear transformations, they preserve vector addition, they preserve scalar multiplication. If I take the transformation of some u plus v, that is the same as if I did the transformation of each of them individually and then added them together. Exact same thing with scalar multiplication. Transformation of the scalar of some vector v is the same as if I took the scalar v times transformation of that vector. And I guess I can combine the two and say the transformation of lambda u plus mu v is, and I just split it using all my rules from above. Hopefully that seems simple enough. I've not introduced anything new here, it's just a lot of the same stuff from earlier. So, let's start using it. Consider the mapping P2 to P3, and it's defined by this mess. I want to prove that it is a linear transformation. Well, let's go one by one. So first, I want to prove that it preserves vector addition. So to do that, I will create a new page. So if I have a transformation of, and let's say I just do u and v, then I'll go back to my equation here. That is x squared plus 1. That bit won't change. I might even write it on the next line here, just so I have space. X squared plus 1. Then instead of p dash, I'm going to have u plus v dash of x. And then minus 2x p of x, so it's minus 2x. Instead of p of x, again, it's u plus v of x. This differentiation, I know that the differentiation of the sum of two things, I can just derive each one individually. So this is u dash x of x squared plus 1 plus v dash x of x squared plus 1. And then the same thing on this other side, minus 2x. There we go, that actually helps. 2x of u of x minus 2x of v of x. And each of these I can just group, I can group this bit, and I can group this bit, and then I can group this bit, and I can group this bit. And you can see that is just bringing me back to, I'll do this, x squared plus 1, u dash x, minus 2x u of x, plus x squared plus 1 v dash x, minus 2x v of x. This, if I show you this next slide here, so this is them just adding the two, and then these two are just my transformations of u and v individually. So you can see the original equation up here again. If I just had u here, then that is this bit. If I just had v here, that is just this bit. So it is each of them individually. Does that make sense? So I had some u and v, and then I do a bunch of expanding and rearranging. I get it back to this form. Cool. And then I want to do the same thing for showing it preserves scalar multiplication. And this one's a little simpler, so I won't go through it manually. I take this lambda v, I apply it. Again, if I'm deriving something that's been multiplied by a constant, that constant just comes out, nothing changes. So this lambda comes out here. Same thing with this function here, it just comes out here. I can just factor out lambda completely. It didn't change anything at all. And I'm back to lambda of t of v. Hopefully that makes sense. Preserves scalar multiplication. We already showed that it preserves scalar addition. And so, vector addition. And so I can say that it is a linear transformation. Are there any questions? Cool. So we're going to do another example. So this linear map T, and it goes R2 to R2, and we're reflecting a vector across this root 3x. So some line like this. And I want to show that the transformation of, I want to show the transformation of 1, and transformation of 1, it takes me to these points individually. So the reflection, I can just have this angle here, and I can just add it twice. So I know this is pi on 3, and if I want to reflect it, I will just do that angle twice. And so you can see cos 2 pi on 3, cos sine 2 pi on 3 gets me this coordinate, and then I will do the same thing here. This would be pi on 6. This would be pi on 6. So this would be pi on 6, and I can do the same to find out this point that's been reflected. Any questions with that? Cool. So, the other thing is we can say that linear maps are just matrices. And the way we can do that is some transformation is some matrix times my vector. And how would I find this matrix? Well, it's just what changes to my order basis. So my, whatever, if I had like 1, 0, 0, and I just showed that being applied to each of my things. We're a little short for time, so I'll try and speed through this. For example, if I had a matrix 110, 1, and I wanted to represent this, then this matrix, so this 110, 1, times some coordinate vector v1, v2, v3, produces this linear transformation. And we can do this for a range of linear transformations. This is just one example. That make sense? Yep. So, I think I might quickly go through this, again for time reasons. So, standard basis is 1, 0, 0, 1, and I want to find the matrix that corresponds to this. Well, from the previous part from earlier, hopefully you remember, we actually already found what vector this corresponds to, and we can just use this matrix representation theorem, and it's what happens to, this is my E1, this is my E2, and that forms the columns here. Simple enough. That is just the matrix, and then you can do any matrix multiplication and find the same values or whatever you want. Here, we want to find a specific point t of 4, 5. There is a long way, and the long way is to do what we did earlier. We know we can split it into its parts and bring out scalar factors and apply, each of these individually. We already know what this is from part A, and this is part A, and we can, substitute this, get an answer. But that's really long, it's really messy. The alternative way is just doing matrix multiplication. So A times 4, 5, and we get this, equals this. Nice and simple. Cool. Let's see. I think I might skip over this one. This will still be in, I'll pause on it and I'll show the working for a little bit, so if you revisit the recording you can see it. This is just more practice of everything we'd already seen. This is back to transformations, linear independent. So it's just proving that if I know the transformation of vectors linearly independent, then the original ones are, and you're just using the identity of something being linearly independent, writing like this. And we're showing the converse is not true. And the working here, there's just a counterexample here. And we're on to kernel and nullity, which I believe should be the last little bit. So, kernel is just the solution for this transformation to be equal to 0 vector. Exact same thing I can say it for matrices, so nothing special there. Linear map of T is the kernel of T. Nullity of matrix A is the dimension of kernel T. Same with this for this, and this is just rewriting these two expressions here. That hopefully is fine. It's just dimensions. And again, just remind, this is the solution for this transformation of a vector or whatever transformation, matrix multiplication, same thing, equals this 0. So, if I wanted to find the basis of, looks like there's a question missing. It's all right. That's odd. This is just showing some maple working. You can see there's this code here. and it's just taking this find the basis. We have this, and we can use Gaussian elimination. It gets us this term here. So this is just showing if I have some ax equals the 0 vector, and how would I solve that? This is the solution for all your x values. So this would be like x1, x2, etc., and I guess t. So if I wanted to find a basis, here I know that this of A, and I have it in terms of this, so you notice that here we had T3, T5, those are the only things. I've just decided to call it lambda and mu. Hopefully that's all fine. So yeah, it just tells us that solving the augmented matrix Maple's already done. The code, you can just copy that as here. And here I can just separate these into lambda and mu. And here we have just this equation of a plane. So it's lambda times this and mu times this other vector. And these are linearly independent. And so they make up the span of this. And they also are its basis by definition. Is that okay? I know I've been going a little quick. Is that all right? Cool. Image and rank. Let's see. Okay. So the image is just applying some transformation. Exact same things. Beta, I'm just applying some AX. The rank is the dimension of the image, and same thing, dimension of the image. Same thing for transformation matrices, they're all the same. And then here, this is a nice little property. So the nullity in the rank of A, so again, we had the rank is what we were talking about. The nullity is the number of, non-leading columns in row echelon form, and the rank is the number of leading columns. And so I guess I'll just quickly jump to this bottom bit, the rank nullity theorem. Well, if this is the number of non-leading columns, this is the number of leading columns, then rank A plus the nullity of A should just be the number of columns. Because if one of them is leading and one of them non-leading, the sum of them should be the total number of columns. And then here we have finding a basis for a kernel versus a basis for an image. Basis of a kernel, we solve augmented matrix this. And then the basis for an image can be formed by extracting all column vectors from the original matrix corresponding to leading columns. So there is a question here. For time, I will just show the result that I'm looking at. So here, I have just skipped to this. Here we have some vector D, take row echelon form, and we get to this. You can verify that yourself. Here we have this is a leading column, and this is a leading column. So if I wanted to find the basis of the image, so remember D is some matrix and I can multiply it. If I want to find the basis for the image, I would take this vector, because this first column is a leading column, so I take this vector, and that is one of my basis vectors. This is also a leading column, so I take this vector and I chuck that here, and that's the other one for my basis. And that is the basis of an image. Does that make sense? Okay. I believe there is one more part here. I'm going to have to skip it, unfortunately. I believe that is it from me. I'm going to pass over to Ewan now to do the eigenvalues and eigenvectors.
Cheers, Arun.
Sorry, I think I went a little over time.
No, that's all right.
Can you help?
Just fix it here, right?
Yep.
Where's the... Yeah. You're good, you're good.
Should be pasted on there. I don't know if that's easier.
Sorry?
It's on this. Would you rather have it on overleaf? Can you pull that
No,
up?
no, it's all right, sorry. Don't worry about it.
Okay. It's that.
Hi, everyone. So, let's begin right away on eigenvalues and eigenvectors. So I'll try to be as fast and concise as possible. So, in terms of defining what an eigenvalue and an eigenvector is, right, we can think of, excuse me, we can think of eigenvectors, right, as stated here, as vectors which point in the same or opposite direction when you multiply it by a vector A. Right, so when we multiply our eigenvector V, right, to A, we still get a scalar multiple of v. And that scalar is the eigenvalue lambda. And so this is our little definition here where we have A being an n by n matrix, scalar being part of the field, and v being a non-zero vector in the nth field. Okay, and so eigenvectors will produce vectors which point in the same and opposite direction when multiplied by another vector, and then eigenvalue is the scalar or the ratio which produces that. In terms of calculating eigenvalues and eigenvectors, which is probably like the thing that's most relevant to us, if we want to calculate an eigenvector, we must know that the determinant of our original vector minus some scalar times the identity matrix has to be 0. And so when we try solve this determinant, we'll get something called a characteristic polynomial of degree n in lambda. And this terminology might be familiar if you've done Math 1081, where we solve recurrence relationships. We also get a characteristic polynomial to find the solutions of those recurrence relations. It's a similar sort of vibe in eigenvectors. And so after we find an eigenvalue using this determinant, we can then find an eigenvector by solving for v in this relationship, where we essentially have A minus lambda times identity matrix multiplied by v, but then that has to produce the 0 matrix. So we must find essentially v from there. Moving on. In terms of eigenvalues existing, right, if we have an n by n matrix, we will have n eigenvalues if we have real and complex eigenvalues all counted. They are also counted by their multiplicity. So for example, if you have an eigenvalue of root multiplicity 2, like in this situation here, so let's say I solve the determinant a minus lambda I equals 0, and then I get some sort of polynomial where I'll have some sort of root of multiplicity 2, like here. Then both the eigenvalues are just 1, and they're both counted as eigenvalues. Whereas, right, if you have the second theorem, the independence of eigenvectors, we say if a matrix A has distinct eigenvalues, for each corresponding eigenvector, then we can say that the eigenvectors are linearly independent. And I'll show you more about the relevance about this in the next slide. In the next example we do. Just last little thing here with diagonalization. So if we have A as an n by n matrix with linearly independent eigenvectors, so in the context of this question, for example, right, essentially when we solve the determinant, right, we get only one eigenvalue. The thing is though, we want two eigenvalues, right? Generally we would want two eigenvalues if we want linearly independent eigenvectors. Whereas this resolves out to lambda minus 3 squared. So lambda equals 3 is, and you could call it almost like a root of multiplicity of 2. And so there's only one eigenvalue here, and so the eigenvectors are not linearly independent. So you cannot diagonalize this matrix. And so if we have linearly independent eigenvectors, we'll have an invertible matrix M, so i.e. the inverse matrix M to the negative 1 will exist. And then we'll have a diagonal matrix D such that A equals to M dm inverse. The second thing is with that as well, I forgot to note that eigenvectors and eigenvalues only exist for square matrices, i.e. things of, let's say, this form. Right? This is a 2 by 2 square matrix. And so the thing to remember here is we have a diagonalizable matrix if it has n linearly independent eigenvectors. Moving on to this example, we let C equal to 1, 2, minus 2, 5, so 2 by 2 square matrix. We want to first find the eigenvalues of C, and for each eigenvalue, find the corresponding eigenvector. So if, as we remember from the previous slides, we can find the eigenvalues by computing a determinant. This determinant being the determinant of C minus lambda I equaling 0. C minus lambda I will just be 1 minus lambda, 2 minus 2, and then 5 minus lambda. Because the identity matrix in a 2 by 2 matrix is just 1, 0, 0, 1 here. And so when we calculate the determinant of this matrix equals 0, we'll then have 1 minus lambda, 5 minus lambda, minus 2, 2 equals 0. And this should give us the polynomial, so I'll just expand it immediately. Lambda squared minus 6 lambda plus 9 equals 0. You can simplify this to lambda minus 3 squared equals 0, and thus solving this, we have the eigenvalue lambda equals 3. So there is one single eigenvalue for C. In terms of finding the corresponding eigenvector for this eigenvalue, right, we had C minus lambda I times our eigenvector V. So when we do matrix multiplication here, this has to produce the 0 matrix. And so with that, we sub in our value of lambda in this situation. So we have C minus 3 times the identity matrix. V produces the 0 matrix. From here, you can pretty much solve an augmented matrix with 0. So first, I'm just going to quickly find out what C minus 3i is. So that's just 1 minus 3, 2 minus 2, 5 minus 3. So that would just be minus 2, 2, minus 2, and 2. And so we want to solve this as an augmented matrix with the 0 matrix. Oh wait, oops. And so if we row reduce this matrix with the, our beautiful software Maple, right? We will row reduce this to this solution here, minus 2, 2, and 0, 0. Which pretty much implies to us, when we are trying to find V1 and V2, where our eigenvector is V equals to V1, V2, we can see that immediately that V1 equals V2. But this 0, 0, 0 row, what that tells us is that V1 and V2 can pretty much take any value. So we just let it equal some constant, t. And thus we can conclude that our eigenvector for the eigenvalue, lambda equals 3, is V equals to T11. Are there any questions about that? All right, moving on to the second part of this question. Is C diagonalizable? Now, the condition I stated earlier for a matrix to be diagonalizable is that for the matrix C, we must have linearly independent, right, eigenvectors. Now, in this case, right, C is a 2 by 2 matrix. So we need 2 linearly independent eigenvectors. As we see earlier, we only have one eigenvector here. Or technically 2, right? But they are not linearly independent. Now, in the context of two vectors, they are only linearly independent if you can't express one as the scalar multiple of the other. And obviously, we can express T11 as a scalar multiple of T11. And so, this is clearly not linearly independent, which means this is not diagonalizable. Any questions about that? Great. Moving on to powers of matrices, right? We can see here that AK equals just A times A times A times A, where A just equals the MD M inverse. In terms of adding like a little extra step to contextualize why this occurs, this equals MD M1M, so you can just do a little smart grouping here, and then D M1M again, all the way up to the very end, where we have M inverse at the end here. Now, we know that M inverse times N is just the identity matrix. So all of that resolves out. We have D K times, and then we are left with the M at the start and the M inverse at the end. Just with a little bit of grouping. This is the identity matrix. And so, if we have any problem involving the powers of matrices, we can simplify it with this method. And so, for example, if we have dk being, this is an eigenvalue, and this is another eigenvalue, we find that d to the k is just the eigenvalues taken to the power in the 2 by 2 case. So if we want to evaluate A4 using eigenvectors, right? Because what we can normally do, right, is take a squared equals a times a and then do like a squared times a squared. So if you want to avoid doing that, we can instead use eigenvectors here. First, right, you want to determine the eigenvalues and the eigenvectors because you need to find the eigenvectors first, right? So the eigenvalues, again, it's the same system of solving. Determinant of A minus lambda, our eigenvalue, times identity matrix has to equal 0. So A minus lambda times the identity matrix will just be 2 minus lambda, 1, 2, 3 minus lambda. The determinant of this has to equal 0. And so our characteristic polynomial, as we see here, resolves out to, and we can factorize in the end, becomes lambda minus 4, lambda minus 1. So if we solve for this characteristic polynomial equals 0, then we'll find that our eigenvalues are lambda equals 1 and lambda equals 4. Using our beautiful software Maple again, right? Now we have to find this matrix here for lambda equals 1 and lambda equals 4. And we find our eigenvectors. And this has to produce the 0 matrix in the end. And so we find our eigenvectors of 1, 1 and minus 2, 1. Notice immediately, minus 1, 1 and minus 2, 1 are linearly independent of each other. Because you cannot express minus 2, 1 as a scalar multiple of 1, 1. So we have two linearly independent eigenvectors here for this 2 by 2 matrix, which means A is diagonalizable. So if we diagonalize the matrix, right? Probably should have mentioned this earlier, but M is just our eigenvectors, right? Placed on each other, and then D, right? The diagonal matrix D is just our eigenvalues in a diagonal. And these are just our eigenvectors. We can find M inverse, again, just using our lovely computer software, Maple, or MATLAB if you do 1251, right? And then, finally, right, we use our multiplication formula, where A4 just equals to M D4 M inverse. And if we multiply all these matrices together, in the end, we'll get 86, 85, 170, 171. Again, you can just use software for this part. Moving on, we'll start to do a little example now. So real n by n matrix A has n distinct eigenvalues, lambda 1 all the way to lambda n, and can be expressed as M inverse dm, where M is an invertible matrix and D is a diagonal matrix with lambda 1, so on and so forth, lambda n is diagonal entries. So we are given a diagonalizable matrix already because we have n distinct eigenvalues, which produces n linearly independent eigenvectors. So first, it asks us to write the characteristic polynomial p of x of A as p of x equals x to the n plus a to the negative 1, x to the negative 1, so on and so forth. And then it asks us to replace the variable x with the matrix D. So it's actually inputting the matrix D into the polynomial. And then for it to be a proper matrix, we can't just leave a constant here. So we replace A0 with A0 times identity matrix. And so we want to first prove that P of D equals 0, the 0 matrix. And so, with that, what we have is P of x equaling x to the n plus a to the n minus 1, x to the n minus 1, all the way to plus a1x plus a0. Note that lambda 1 all the way to lambda n as our eigenvalues are the solutions to this polynomial. Because by definition of eigenvalues. Because this is essentially the characteristic polynomial we are getting when we compute our determinant. I'll just call it C minus lambda I equals 0. So since this is the characteristic polynomial, if we compute any of our eigenvalues, lambda 1, lambda 2, all the way to lambda n in, it will give us 0. And so we replace now x with d. So you find that p of d is d to the n plus am minus 1 d to the n minus 1 all the way to a1d plus a0i. So replacing a0 with a0i because it must be a matrix. Now, we know that every term in the polynomial must be a diagonal matrix because D by nature is a diagonal matrix itself, which means P of D is a diagonal matrix because all of these individual terms are themselves diagonal matrices. And so because we have D of K being the diagonal matrix with entries lambda 1 to the K all the way to lambda n to the K, we'll have kth entry of D being lambda to the n, lambda subset K to the power of n plus an minus 1 lambda k n minus 1 all the way to a1 lambda k plus a0. This, you might notice, is just our characteristic polynomial. And so since the eigenvalues are the solution to p of x, as we identified earlier, it means every term in the matrix p of d will also be 0. And therefore we have P of D being the 0 matrix because all the terms produce the characteristic polynomial. Any questions about that? Great, so that's the kind of the first part. Now we are asked to prove, hence or otherwise, prove that P of A equals to 0. Now you can use, probably there is some other method, but the most kind of intuitive thing to me is just to use the previous part, right? And so let's prove P of A equals to 0 using the previous part. Well, first, I know that A to the K equals MD K M inverse. So just note that for now, because that's our formula from before for when we have powers and matrices. When I calculate P of A, this will just be P, of MD M minus 1. Because we realize this matrix A is a diagonalizable matrix, so we can express it in the form of a diagonalizable matrix, MD M inverse. And so what this will produce for us is M dn M inverse, so it's just subbing it into each term, plus a to the n minus 1, M dn minus 1 M inverse, plus all the way to a1 M d M inverse, plus a0i. We can immediately take out M and M inverse out of everything because it is common to all the terms. And so we will have d to the n plus a to the n minus 1 d to the n minus 1 all the way to a1d plus a0i. M inverse. Notice here that this is just P of D. So we'll have M P of D, M inverse. And since, as we proved in part 1, P of D is the 0 matrix, then we'll just have the 0 matrix here as well. So that's how we prove P of A is also the 0 matrix. Last part. Using the result in 2, show that the matrix 2, 1, 4, negative 1 satisfies A squared equals to A plus 6i. And so with that, let's let A equal to 2, 4, 1, negative 1. Then to find our characteristic polynomial, it will just be P lambda, which will also be the determinant of A minus lambda I. The determinant of A minus lambda I is just the determinant of this matrix 2 minus lambda for 1 minus 1 minus lambda. Taking the matrix here, we will have, eventually we will get lambda squared minus lambda minus 6. And this is immediately factorizable as well. Lambda minus 3, lambda plus 2. And so, from the previous part, we know that A is a matrix solution of the characteristic polynomial, because we proved that P of A produces the zero matrix. So A is a solution, which means, right, this means this is not that relevant. In the end, we'll have A squared minus A minus 6I becoming the zero matrix. And so this thus satisfies A squared equals to A plus 6I. And this is simply just because P of A equals to the zero matrix. Any questions about that? Now, one of the classic applications of eigenvectors and eigenvalues is solving systems of differential equations. So here's the proposition. We have an n by n matrix, A. Then we will have y of t equaling e of lambda t times the eigenvector will be a non-zero solution of the differential equation dy on dt equals to ay. If and only if A has eigenvalue lambda and eigenvector v. Which means the general solution would take this form here with constants a1 all the way to an, n eigenvalues from lambda 1 all the way to lambda n, and then we'll have our corresponding eigenvectors v1, v2 corresponding to the eigenvalues lambda 1, lambda 2 all the way to lambda n of A. That will make a lot more sense when I actually attempt the question. So let's take the first order ODE first. So I'm going to first define our y as the solution, like a solution vector, let's say x, y, right? Because we want a solution for x and we want a solution for y from this system of differential equations. Then I'll also define A as our coefficient matrix, i.e. the coefficients of these terms. So it'll be 4, 1, minus 2, 1. And so we've now established the system dy over dt equals to ay. So first, let's try solve for the eigenvectors of this system, which means we first have to find the eigenvalues. So the determinant of A minus lambda I would just be the determinant of 4 minus lambda, 1 minus 2, 1 minus lambda. So calculating this and then simplifying would give you lambda minus 2, lambda minus 3, which means our eigenvalues are lambda equals 2 and lambda equals 3. For lambda equals 2, again, using the same process where A minus lambda I, V equals 0, I'm just going to imagine I've already MATLAB or mapled this, right? Solved for this matrix. But lambda equals 2, we will have the eigenvector V equaling T of 1, 1. And then for lambda equals 3, we get the eigenvector T 2, 1. So now we have two clearly linearly independent solutions because 2, 1 cannot be expressed as a scalar multiple of 1, 1. And so our two solutions are y equals e to the 2t 1, 1 and y equals e to the 3t 2, 1. In general, our general solution will be a linear combination of these two solutions, which means our final general solutions will be a times, so some constant a, times e of 2t, 1, 1, plus b times e of 3t, 2, 1. And so this is one of our general solutions. And so, because y equals to xy, then we'll have our final solutions to the differential equation, x equals ae 2t plus 2b e 3t. And then y will just equal to ae 2t plus b e 3t. So just equating the x and y components. And this is for a and b as being real constants. Now you might ask where this comes from. It comes from literally the proposition in the previous slide here. Where we have y of t equaling e lambda t, where lambda is our eigenvalue, right? And as you can see here, our eigenvalues are 2 and 3. So those pop up as our non-zero solutions of this differential equation here. And then this is our eigenvector. Moving on, we'll now do the higher order ODE, which is a second order one. So with this one, right, we kind of need to do some, how do I say, smart substitutions, right? Because what we just established is that we know now how to solve first order differential equations using eigenvectors. And so what I'm going to do now, algebraically, is to find a clever way to turn this system into a first order system. And so how will I do that? For first, I'll let y1 equal y and y2 equals the dy on dt. Right, so I'm just going to define two variables, y1 and y2, where y1 is y and y2 is dy on dt here. Then what we'll have, right, is a first order system where we take it with respect to these two variables, y1 and y2. Now, dy1 on dt is just dy on dt. And dy on dt, we've defined as y2. So it essentially is just 0 times y1 plus y2. Whereas with dy2 on dt, if we look at the previous equation, dy2 on dt would be d on dt of dy on dt, which is just the second derivative here, d squared y on dt squared. And so we know that the second derivative equals 2 dy on dt plus 24y, which means we will essentially get the equation 24y1 because it's y plus 2y2, where y2 is just dy on dt. So see how this just goes to the other side essentially, and we express it in terms of our new variables. Now all we have here is our first order system. And so now we can write this system as dy over dt equaling ay, but this is where y is just y1, y2. So now we're going to solve for y1 and y2 to get the solution of the differential equation, right? And then we'll have A as our coefficient matrix, which would now just be 0, 1, 24, 2. So now we just have the same thing as the first question, just with different values. So now if we solve this coefficient, for the eigenvectors of this system here, what we will get is that the eigenvalues computing determinant of A minus lambda I equaling 0, we'll find that our eigenvalues are lambda equals 6 and lambda equals -4. And so this will give our eigenvectors for lambda equals 6, we'll have our eigenvector alpha times 1, 6, so just some scalar times that. And then for lambda equals to -4, we'll have v being alpha times 1, -4. And thus, our general solution takes this form, y1, y2, will just be a linear combination of these two eigenvectors here, which is C with E6t, right? Again, calling back to this non-zero solution here. So we take E of our eigenvalue times t, and then the eigenvector itself. So we have C E6t, 1, 6, plus D times E negative 4t, 1, negative 4, is our general solution. And so, since we know that y is the variable we are trying to solve for in this differential equation, that means, right, y1 is our solution because we set y to be y1, right? So the solution for y will just be the value of y1. So just equating that across, we'll have our general solution CE 6t plus DE to the negative 4t. Because we set y to be y1. No questions about that? All right, moving straight on to probability and statistics. One of my great favorites. For context, I do actuarial studies, so this is going to be like the rest of my degree, fortunately. I'll try to blast through this kind of theoretical section as soon as possible. You guys are not year 11 students. I'm sure you guys understand these concepts, right? Probabilities lie between impossible and certain. Impossible being a 0% chance of it happening, and then a full 100% chance of it happening. So all probabilities have to lie within that domain. The probability of the null set is 0, and then the probability of S is certain for this sample space S. If we have disjoint, otherwise known as mutually exclusive, A and B, then we'll have P of A union B being PA plus PB. Because if we express this in terms of event diagram, mutually exclusive events cannot happen together. If one happens, the other cannot happen. So the probability of A and B happening, right, is just PA plus PB. So some fundamental things, the probability of the complement event. So for example, if I have, for example, at least one student winning, the complement of that is no students winning. And sometimes that is easier to calculate than it is to calculate at least one student winning, right? Because if we have one student winning being our thing we have to calculate, then we have to calculate the probability of one student winning, 2 students winning, 3 students winning, all the way up to like the nth case of students winning, which is extremely inconvenient to us. So instead we can take the complement case where we do 1 minus the probability of no students winning. We calculate one probability, much better, much faster. In general, if A and B are not mutually exclusive events as well, we have to have our addition rule here, PA plus PB minus PA intersection B. The reason being that P of A contains P of A intersection B. So we've essentially added it twice in both P of A and P of B. So we have to remove it. So we have two, we've double counted it, which means you have to remove one. And if A is a subset of B, then the probability of A is less than the probability of B occurring, because all elements of A are a part of B. So B is the greater kind of set of events. And if S is finite, then pretty much what that means is just the sum of all probabilities is 1 for a certain event. Moving on to conditional probability. So let's say I have A and B being events within a sample space S, and that the probability of B is not 0. Then we have our formula, probability of A given B being equaling the probability of A and B occurring, and then P of B. Now you can also see this through a Venn diagram as well. So let's say this is A, and let's say this is B. Let's say the probability of B has already occurred, because that's P of A given B, right? B has already occurred. So we are only concerned with this, which means the probability of A occurring lies in this intersection here. So we just find the proportion of B occurring where A also occurs. So it's P of A and B over P of B. That's why that formula happens. And so seeing a tree diagram also helps us observe this case. Some important rules within conditional probability. P of A and B equals the probability of A given B times the probability of B. Because you can essentially put P of B on the other side and you'll just have P of A given B. Our conditional probability from this previous slide. And then it's algebraically equivalent here. If B1, B2, and all the way up to Bn partition S, so what means by partition is that if you have all of these separate events, B1, B2, all the way to Bn, they make up all the events possible within S. Then we have our total probability rule, where the probability of A is the probability of A given B1 times the probability of B1, plus the probability of A given B2 times the probability of B2, plus all the way up to the probability of A given Bn times the probability of Bn. Because B1, B2, all the way up to Bn make up all the events in S. And so the probability of A occurring, right, will just be adding up all the probabilities that A occurs, given that this B1 all the way up to Bn occurs. So you have to add all those separate probabilities up. This will make more sense in the context of a question. And also we have Bayes' theorem as well, where you can express, also you can kind of see from the multiplication rule here, that P of Bk given A equals to the probability of A given Bk times the probability of Bk over the probability of A. And so now, it's not. I was expecting a question, but it's not quite a question. Last little thing, hopefully. Yes, last little thing here is just talking about independent events. We define independent events if they satisfy the condition where both of them occurring is just the product of their probabilities. Where P of A and B just equals to PA times PB. So this is the definition or the condition of proof for mutually independent events. So you can kind of consider it as like an if and only if situation. Moving on to an example. So we have a particular diagnostic test being 99% correct when a person has the disease and 95% correct when a person does not have the disease. In a population, 2% have the disease. Compute the probability that the person has the disease given that the test was positive. Now, for this one, right, it's a conditional probability because we are given that some event has already happened. The test is positive. We are given that. And so we have to use our conditional probability formula. That's kind of going to be our method here. So now the only problem is, what are these probabilities in reality, right? So P of A and B is quite simple to compute. Why? Well, it's just the probability that the person has the disease and that the test is positive, which is essentially just 0.02 times 0.99. So this is the probability that the person has the disease, and when they this is the probability that the test is correct when the person has the disease, given as 99% here. And this is the probability that they actually have the disease in the first place. Right? You can also kind of express this as P of B given A times P of A, which is just Bayes' theorem as well. Because this 99% is literally P of B given A, where A is given the given event where they have the disease. And so B is the probability is the event that the test is correct. So this is 0.99. And then the probability that they have the disease is 0.02. So this is over P of B. So the probability that the test is positive. Now you can use the law of total probability, right, to find P of B as P of B given A times the probability of A plus the probability of B given that A didn't happen times the probability of A. So it's essentially the probability that the test is positive when the person either does have the disease or does not have the disease. So to add up all those scenarios. And so what I get here is 0.02 times 0.99 over, now I just calculate each of these probabilities. So this will be 0.99 times 0.02 plus 0.05 times 0.98. Because in P of A, B, given that they don't have the disease, we are given, right, that it's 95%, so to take the complement case there. And then also, P of them not having disease is 98%. So now we just compute all these probabilities in, and then we eventually get the probability 0.288. 2 free decimal places. Any questions about that? Right, and so if you draw a tree diagram, it represents all these possibilities, where D is the event that someone has disease, and T is the event that they test positive for the disease. So this is the event where they test negative and they don't have the disease, so it's good. Then this is the event where they test positive but they don't have the disease. Very bad, right? Also, not good would be when they test negative but they actually have the disease, and then they have the disease and they test positive, which is good. Moving on to this question. This is from a final. So we have urn 1 containing 3 balls, 3 red balls and 4 blue balls. Urn 2 contains 4 red balls and 2 blue balls. And a ball is drawn at random from urn 1 and placed in urn 2. And then a ball is drawn at random from the 7 balls now in urn 2. Firstly, what is the probability that the ball drawn from urn 2 is blue? So if we construct a tree diagram with all the possibilities, we firstly have the probability of the first ball being red, or the probability of the first ball being blue. Now, for urn 1, we have 3 red balls out of 7 in total, and then 4 blue balls out of 7 in total. So it's just 3 on 7 and 4 on 7. And then these represent all the other probabilities, where, given that R1 has already happened, so the first ball drawn from urn 1 is red, then the probability that the second one is also red is now 5 on 7. Because now, instead of 4 red balls, if we take out a red ball from urn 1, we now have 5 red balls and then 2 blue balls. So in total we have 7. So now that probability becomes 5 on 7, as we see here. And so, with these probabilities, we can now compute each of our questions. What is the probability that the ball drawn from urn 2 is blue? Well, if we want urn 2 to have a blue draw, then it's these outcomes which are favorable to us. So multiplying these probabilities together, what we'll get is 3 on 7 times 2 on 7 plus 4 on 7 times 3 on 7, just by the law of total probability, where we have probability of B2 being the probability of R1 times the probability of B2 given R1 plus the other thing. So we either have this path here or we have this path here. This will give us a probability of 18 on 49 for the first part. Now we have to calculate a conditional probability here. Given that the ball drawn from urn 2 is red, what is the probability that the ball transferred was blue? So we have to find the probability of B1, so the first ball being blue, given that the second ball drawn was red. So by Bayes' rule, we have P of R2 given B1 times by P of B1 over the probability of the second ball being red. Now, the probability of the second ball being red, you can express as another law of total probability here, where it's this path, and again, it's this path. And so this will give us 4 on 7 times 4 on 7 over 4 on 7 times 4 on 7 again, plus 3 on 7 times 5 on 7. So it's just multiplying all the probabilities I found in my tree diagram. And this will eventually just equal to 16 over 31. So it's just one application of Bayes' rule here, given these two events. Now, the third question, let A be the event that the ball drawn from urn 1 is blue, and B be the event that the ball drawn from urn 2 is blue. Are A and B statistically independent? Which is, so basically it's asking, right, are they like independent events per se, right? Which means, what is the condition for independent events? Well, we want P, so just for any two events, A and B, we want P of A and B being P of A times P of B. Which means we can state that they are statistically independent if they satisfy this condition. So let's check that it actually does. So P of A and B in this case, right, will be 4 on 7 times 3 over 7. Right, so essentially, we want the event that urn 1 is blue, and then urn 2 is blue. So we want blue and blue, essentially, which is 4 on 7 times 3 on 7. So that's probability of A and B. Now, we need to check this is equivalent to the probability that it equals A and the probability that it's B. This, you'll find, the probability of A is 4 on 7, and the probability of B is 18 on 49. How do I get those? Well, if A is the event that urn 1 is blue, right? Urn 1 is blue in these situations. These ones, right? So it's essentially 4 on 7 times 4 on 7 plus 4 on 7 times 3 on 7 by the law of total probability. And then urn 2 being blue by itself as well are these situations here. So again, you can calculate another law of total probability to simplify to this fraction here. But you will notice that these two things cannot be equal, which means these two events are statistically independent. Oh, sorry, are not independent. Sorry, my apologies. Any questions about that? Now, let's talk about random variables, because this will eventually kind of flow into a discussion about probability distributions, right? So a random variable is essentially a function, right, which maps outcomes, right? So outcomes, for example, flipping like a heads on a coin, right, or rolling a 1 on a dice, right, to actual real numbers. So in the context of actual questions, right, if we set an experiment where essentially we're flipping coins and then finding how many heads we're getting, the random variable x, we would let it be the number of heads we get. And so since it's a number of heads we get, we're essentially assigning an outcome to a number. So essentially, if we calculate P of x equals 1, we're calculating the probability that we get heads once in the experiment. So that's what a random variable kind of does to us. I've got to speed things up. So a cumulative distribution function, whereas, measures the probability of having up to a certain outcome. So for example, the cumulative distribution function is defined as P of x, or the random variable x, is less than or equal to some outcome. So it's the probability up to a certain point, essentially. You can consider it that way. And some properties include that if A is less than or equal to B, right, then f of A is less than or equal to f of B. And if A is less than or equal to B, then we can calculate the probability between A and B to be f of B minus f of A. And then as we approach negative infinity, the cumulative probability should be 0. And as we approach positive infinity, the cumulative probability should eventually be 1. Right? Because all of our probabilities should add up to 1 in the end. And then at the start, we have nothing. So what a probability distribution is, right, is essentially a function, right, which maps the random variable, right, to the probabilities of all events associated with such a random variable. I.e., we have P of x equaling some number of outcomes. And to form a valid probability distribution, it must satisfy two conditions. Every single probability must be greater than or equal to 0. And the sum of all the probabilities has to be 1. The expected value is a measure of central tendency, where we essentially calculate this using, right, a weighted mean. Essentially, we take all the different outcomes, right, and we weight them against the probability that they occur. If we add all this up, we get a value that we kind of expect to occur. And a convenient little trick with the expected value function is that we can input a function of the random variable x inside so that the outcome is g of xk. Moving on to variance. Variance is another measure of central tendency. So essentially it measures the spread from the mean. That's what variance measures. And so it's defined as the expected value of the distance from the mean, so x minus the mean, so the distance from the mean squared. And this is also defined as a standard deviation squared. So a formula we use to calculate variance, right, especially when we're not given standard deviation, is just e of x squared minus e of x itself squared. We can shift and scale a random variable within the expected value and variance functions as such. Now this manifests because you see the e of x squared minus e of x all squared. That's the formula for variance. That's why you get a squared constant on the outside. You can compute that yourself though. Now, what a Bernoulli trial is, right, is essentially an outcome where we have a success and a failure. So for example, if we consider flipping a heads on a coin a success, then the probability of the other thing, which tails occurring, is 1 minus the probability of our success. That's called a Bernoulli trial. So we have a success and a failure. And so the number of successes is defined as P of x equals k equals to nck, pk at q, and minus k. Now you might notice that this ends up being the distribution of the binomial distribution. The binomial distribution is essentially just taking n amounts of Bernoulli trials, and from that you can measure how many successes and failures there are. And so we are given our expected values and variance formulas where e of x is the number of trials times the probability, and then the variance is that e of x, right, times weighted against the probability of a failure. Wow, we have quite a bit left. So I'm going to try speed run through this. I apologize. Right. So I'll just try to get through all the content. So geometric distribution is kind of similar to the binomial distribution. But instead, the distribution measures, right, the probability of a success occurring after a certain amount of failures. So essentially, right, if we take the CAPE trial, we want that trial to be a success and then every other trial to be a failure before that. And so it has expected value 1 on p and variance q on p squared, where q is just 1 on p. So we can use sign tests to see whether we can, the event or the probability of the event that you're measuring, right, is just pure luck or not, right? And we use the test usually based on 5%. So it's kind of like a p-value if you've seen that before in statistics. So a probability density function, right, is very similar to a probability distribution to a probability mass function, except probability mass function is assigned to discrete random variables, but probability density functions are assigned to continuous variables. And so if I have x being a continuous variable with cumulative function f of x, then this being the probability density function is f dash, so the cumulative density function. It's the derivative of the cumulative density function. And so we know that our probability density function has to be greater than or equal to 0. Because for it to be a valid probability distribution, all the probabilities must be greater than or equal to 0. This is just another definition of the cumulative density function. And this shows us that the sum of all the probabilities has to be 1. And then we can also use a definite integral to calculate the probability between two outcomes. For a continuous random variable, you cannot compute the probability at one particular point. You must compute a range. So expected value is calculated in a very similar way, right? Except instead of a sum, we have an integral. And an integral is a sum in a sort of way, because you can define it as a Riemann sum with infinite rectangles. Probability density function. Let's just move on to the normal distribution, because I think you need this slide first before you move on to that, right? So the normal distribution is essentially this continuous random variable here with the probability density function phi x equals to 1 over the standard deviation root 2 pi e of negative half x minus the expected value over the standard deviation squared. And so this is for the general normal distribution, where we have parameters, right, of the mean and the standard deviation squared, otherwise known as the variance. If we have a standard normal distribution, our mean will be 0, so right at the center, like this, and then the variance will be 1. So these are our parameters for a standard normal distribution. In terms of calculating normal probabilities, we are given a Z table of the cumulative density function of the normal distribution. Meaning that whenever we have a normal variable in general, we want to standardize it to the standard normal distribution using the formula Z equals to x minus mu over the standard deviation. So in this way, we can compute the Z, almost like a Z score. And so we find our probability in this form here and then use the table. We can also normally approximate binomial distributions. When we have a large enough number of trials in the binomial distribution, it will converge due to something called central limit theorem, which I won't go into, right? Where it converges to a normal distribution. And so in certain questions, we use normal to approximate for binomial. And that's kind of, that's it. Thank you guys for coming. So thank you, we'll pack up. Man, that's hard to cover.